In this sequence, we're going to talk about the image classification problem and some image classification data sets. So the reason why I would like to talk about this early on is my personal preference to start with some specific examples and also explain some examples in details. So the hope is that by having a more detailed understanding of one particular problem that we will often refer to, and also more specifics about how exactly these data sets look like, this will help you better to understand other concepts in the course. As literature, there are the course notes of CS 231N from Stanford, and you can just click on the link in the PDF and you will get to the course notes. I wanted to briefly show that on screen as well. So here's how the website looks like. There's a bit more information and maybe a bit different information, but you will see that if you read this, this follows pretty much what I'm going to talk about in this sequence. So for the image classification problem, as input, you're given an image with a width W, height H, and C color channels, where C is typically 3 for red, green, and blue. So you could say that a floating point image I is an element of R to the power of W cross H cross C. So if W is 1000, the width is 1000, the height is 1000, and there are 3 color channels, then we would have 3 million values. Often, floating point images are given in a range where all values are between 0 and 1. So you could also say that I is C in the interval 0 to 1 to the power of W cross H cross C. For other image formats, the individual values are often given as 8-bit integer, so 8 bits per channel. So then the image would be this 8 bits, 0 to 255 to the power of W cross H cross C. And as output, what you would like is to assign a class label from a set of labels L, for example, cat, dog, hat, mug, and whatever else. There's a difference between assigning only a single label per image or multiple labels per image. So these are slightly different types of problems. Maybe the easier one to start with is to assume a single label per image that has to be assigned. Now, here is an image of a cat that we might want to classify. Why are we talking about cats? It's just for some reason the internet is full of cats and cat videos, and it's a reasonably nice example to explain the problem. So if you look at the cat image to the left as a human, you have an immediate understanding of the image and you can process the image really, really well. If you look at the same image to the right, where you just now see the image as a matrix of color values, in this case maybe this is a single channel grayscale image, then you will notice that your brain has no ability to understand the image from this matrix of values. And what the task is of image classification is basically you take this matrix of values that you see to the right, and you ask the computer to assign a label, and typically as output you will have some intermediate output that assigns something that's more like a probability per label. So it would say maybe 82% is cat, 15% dog, 2% hat, and 1% mug. And then as the final output, you simply pick the category that has the highest probability. In this case, this would be a cat. Now, as discussion, the problem is trivial for humans and in some sense very difficult for computers. If you just look at the image as area of numbers, this gives you some intuition why it's so difficult. And so the image can be described by millions of values, but maybe if we go back, then it's maybe not anymore, thanks to deep learning, that the problem is very difficult for the computer, but it's very difficult for a human to describe to the computer what to do in order to classify an image. So if you look at this matrix of values to the right, then the question is, you want to write some heuristic or give some instructions to the computer how to look for a cat. So you might say, well, maybe we look for a big blotch of gray values. But if you do this type of, give this type of instruction and write some small program to look for a blotch of gray values, then you also detect a gray shark and a gray cloud. And in addition, there are lots of cats that might be black or white that then you don't capture. So then you say, well, the cat has these yellow eyes. Maybe let's look for some yellow circles. But then again, you find some yellow circles, but maybe a tennis ball is also a yellow circle. So it's very difficult kind of for a human to give instructions what exactly makes a cat. And even for the human itself, you can look at the image to the left and say, this is trivially a cat, obviously a cat. But how can you describe even to yourself, what did you do in order to come up with this decision? So how did you recognize this as a cat? And the answer that you will be able to give is, well, it obviously looks like a cat. But you will not be able to describe your thinking in the sense of, well, it's kind of fluffy. Well, it could be a cloud. It's just the texture of the fur. But then again, what exactly about the texture made you think this is a cat? It's very difficult really to describe to yourself how did you make the decision that this is a cat. All right, so some basic image processing. So let's just assume for some type of neural networks that you could actually take this matrix or tensor and convert it into a long vector of numbers. So in this case, you would ask the computer just to classify a long vector, and the vector describes the image of a cat. So in this course, we will needlessly switch between representations describing images as matrices, as tensors, or as vectors. There will be some more details in a future lecture about these type of conversions, and maybe also the Python commands that conduct these conversions. So here are several challenges of the image classification problem. First, there are viewpoint variations. A single instance of an object can be oriented in many ways with respect to the camera. So I'll need to switch back and forth a bit. So for example, here there's some statues, but you can look at it more from the top or from the bottom. And this makes it very difficult because an object will look different depending on where you take the picture. Scale variation. Visual classes often exhibit variations in their size. So that is size in the real world, not only in terms of their extent in the image. So you could think of a boat, for example. There's a small fisher boat for 2 people, and there's a huge cruise ship that is fitting 5,000 people. So this is a large human basketball player, and this is a small human actor, and you see that their size difference can be very big, but of course in other instances, such as boats or maybe even buildings, these differences can be even much larger than that. Deformation. Many objects of interest are not rigid bodies and can be deformed in extreme ways. Here we go to our typical cat example. A cat can kind of orient and twist and deform its body in many, many different ways. So here you see an extreme pose that the cat can make, and its body, you might say, well, of course the head is on top, but here the head is in the middle, and then some legs are on top and some legs on the bottom. So it's there are a lot of extreme poses like that. Yes. All right. Occlusion. The objects of interest can be occluded, so sometimes only a small portion of an object could be visible. So here we see our cat again that is partially occluded by a wall. But there are other types of occlusion, not where maybe half the object is visible, the other half is not visible. You could have maybe a cat that is behind a bush, and then the occlusion is kind of everywhere, just a little occlusion everywhere, and so there are different types of occlusion. Illumination conditions. So if you have an image taken in bright daylight, it might look different than an image taken in the dark. It might look different than an image taken inside a building. So here are some different examples of I guess these are statues of penguins, and you can see on the left here, this is a very different type of illumination than the middle or the right, and so the colors will change, like the values, colors in sense of the pixel values that you will get in the same part of the object will be very different. Background clutter, so the object of interest may blend into the environment. This makes them hard to identify. So for example here, the cat looks very similar to the fabric the cat is sitting on, and it will be very difficult to find the outline of the cat because the pattern on the fur of the cat is similar to the pattern in the background. And intra-class variations. Now a class can be very broad, but then within the class you have objects that can look very different. So for example, if you look for chairs, there are some traditional chairs. We'll know what they look like, but then maybe a designer makes these crazy chairs such as this one here, or this one here, or this one here, that as a human is very easy to recognize, hey, this is a chair. But this intra-class variation can be very large, so maybe it's difficult to get examples that represent even these extreme variations within a class. So now we're going to look at one particular dataset. This is a bit smaller dataset, and it's called Cypher 10. Cypher 10 consists of 60,000 images that are a bit smaller. So the images are of size 32 × 32 width and height, and they have 3 channels RGB. So if we multiply this together, then we have 3072 values to represent one image. And we have 6,000 images per class, and each image belongs to only one class. Now, how many classes are there? As you can guess, there will be 10 classes, and Cypher 10, the name indicates the number of classes already. Then there's a fixed split of 50,000 training images and 10,000 test images. The 10 image classes are airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. And the test images have 1,000 images per class. So this is an example of a really well-balanced dataset, and you could think about this as something like the Hello World dataset of deep learning. And with this dataset, you can train a model from scratch, and you can get some reasonable results. So here are some examples of this dataset. You will notice that 32 by 32 spatial resolution is not that high. You will be able to recognize the objects somewhat, but the details are completely missing, and often you will find that the lack of details, even for you as a human, makes it very difficult to decide what an image shows. For example, like here, this is an airplane, but is it really obvious that this is an airplane? This could be a scratch on some metal, or this could be a tiny spot of rust on some material, maybe some scratched paint. It's not really that obvious. Other things, this one, a deer, tough, I don't see it. Just see like a brown splotch. Or some of these frogs here, this one or maybe this one. If I tell you it's a frog, you can see it, but if I just show you the image and you have no idea even about these 10 classes, this is difficult to recognize. So there's a related data set called Cypher 100, and Cypher 100 is similar to Cypher 10. Now we have 100 classes with 600 images per class. That means the dataset doesn't get a lot bigger, we just have a lot more classes and fewer images per class. There are 500 training images and 100 testing images per class, and the 100 classes are grouped into 20 superclasses. So one superclass, for example, is aquatic mammals that have beaver, dolphin, otter, seal, and whale, and another superclass, fruit and vegetables, has apples, mushrooms, oranges, pears, and sweet peppers. Now then, let's look at some other things. Maybe people is baby, boy, girl, man, woman, and there should be something related to maybe medium-sized mammals, fox, porcupine, possum, raccoon, skunk, or large outdoor scenes, cloud, forest, mountain, plain, sea. So this should give you some idea. There's maybe some discussion. Let's, for example, look at this vehicles 1 and vehicles 2. So vehicle 1, you have bicycle, bus, motorcycle, pickup truck, train, lawnmower, rocket, streetcar, tank, tractor. And here, the idea is that the superclasses should group objects that are similar to each other, and you would hope that objects that are in one superclass are more similar to each other than an object from one superclass would be to an object in another superclass. But maybe here it might be difficult, like the lawnmower, maybe that is more similar, I don't know, bicycle. These kind of two are smaller. And then if you look at something like streetcar, maybe that's more similar to bus. So what you notice is maybe that this categorization, grouping into superclasses, is actually not that easy, and that requires some controversial discussion, controversial decisions that you might want to actually make differently. So now we discuss Imagenet, and Imagenet is a very significant achievement, and it, in some sense, I would credit Imagenet with starting this whole deep learning hype about 10 years ago. So there are some papers about it. You can just click on the links. So in 2009, maybe a paper to start out. And then in 2015, a paper that's more like a looking back at what has been achieved and some lessons learned. So there's also a website about Imagenet that you can look at that contains a lot of the more information than what I'm going to discuss here. So Imagenet itself has 22K categories and 15 million images, but generally people don't work on this full data set. There has been a subset identified called the Imagenet Large-Scale Visual Recognition Challenge that is a subset with 1,000 object classes and about 1.5 million images. How are you going to get classes to categorize the images? This is a non-trivial problem, because if you just think from top of your head, what classes can you think of? Of course, cat, dog, elephant, giraffe, train, boat. You might have a problem coming up with 1,000 object classes. And then there's the danger that your idea about what classes you come up with might be heavily biased. So what Imagenet actually did is they started with this WordNet database, augmented with 120 categories of dog breeds for showcasing fine-grained classification. So this is again some general warning. Maybe if you use Imagenet, and a lot of people use Imagenet, the dataset is not unbiased. It might have a lot more information about dogs than about other classes. And so then, how were the images annotated? So this was done by crowdsourcing the annotation process. And the annotators were asked to indicate the presence or absence of an object class in an image. Is there a bow in the image, or is there not a bow in an image? And there's some object level annotations that include bounding boxes of the visible part of the indicated object. So if you want to go from image classification to object detection, then these bounding boxes are going to be very helpful. If you not only ask what is the main object in the image, but also tell me where in the image is this main object located. Now, one other comment I forgot before is that this WordNet, I think this has about, there's a question about what is a category and what words are grouped together. So I think they have maybe about 20,000 to 80,000 or 80,000 of these categories, and then the 1,000 classes are just a subset. So if you want to really build an extreme version of this, it seems that you might be able to scale up to something that has even a lot more class labels than 1,000 or even 20,000. So here's just one graph that shows not too recent, but shows a bit of the history of the performance on Imagenet. That is, in the beginning, you had these traditional techniques, and then in 2012 was this major breakthrough, AlexNet, which was a deep learning framework that drastically improved the performance. Now, the performance number here is actually not exactly clear what it is. We just say for now that lower is better. So it went from 25.8% error to 16.4% error. And this was the time where a lot of people got super excited about deep learning and its potential and started to switch. And then you can see rapid additional progress, where from the first deep learning solution in 2012 to 2015, it went down to 3.6% by adding further improvements. And we will discuss several of these networks. A lot of these early networks became very famous. This is AlexNet, this is the first one. Then probably this VGG, Google Net, and ResNet are all very, very famous papers with lots of citations. There is some discussion, is this success of the neural networks now better than a human labeler? And so there is a way to interpret the data to say that actually the performance of a deep neural network is now better than a human, such as what is suggested here in the graph. But this is probably not true in every sense. So to really read exactly what this claim, to understand exactly what this claim means, you would have to go and look at the paper. But I think what you can think about is that under certain circumstances and the right data and the right conditions, then a deep neural network will be able to beat the human in performance. Maybe one example is if you're looking at distinguishing the differences between different dog breeds or cat breeds, you can train the computer to do that pretty well, and then you might be able to beat the human. But if, for example, then the training data will be different from the testing data, maybe we make the images a bit larger, or there's a different camera used, or different noise, then the human is more robust to these type of changes. So if all of a sudden we would have maybe randomly distorted images, or someone runs some crazy image filter over the images, then kind of the idea is the human would be much better in reacting to these type of changes in what type of data you're looking at than the computer. All right, this concludes this section.